Thank you, good afternoon. Thank you, Vibav and Ryan, for the invitation. It's a pleasure to be here at UAI. I like to think that is a little bit more like a field report. It's my perspective, what I want to call, what I have been calling the causal reinforcement learning, that is the relationship or the connection between causality or causal inference and reinforcement learning. This is joint work with Sangak, the postdoc that couldn't be here for visa issues, Justin Zhang, Forney, and Yuda Pearl. First, quick announcement, because I will send the file to Vibav. This is preliminary draft. Contact me if you want to share with others. And first of all, I'd just like to start with an announcement, not the causal reinforcement learning of what I'm doing in my lab, given that I'm trying to find a postdoc, and you are still paying attention. The lab, I think the insight that we have in the lab that is unique and quite simple is that the world can be decomposed in terms of these underlying causal mechanisms that we usually in the field call structural causal model. And I like to think that there are two views that you can take of what's going on in a structural causal model. Structural causal models are always all out there, but in general, you don't have access to it, except for in fields such as physics or chemistry, that maybe takes 100 years, 200 years, and you end up being able to get one of these underlying laws of nature. In general, in the fields that we are very interested, like in the health sciences, the biomedical sciences, or the social sciences, that usually the one that we interface with, AI and machine learning in general, those are kind of complex phenomena that is very hard to get the precise causal mechanism. But they are out there, and the task in causal inference is try to go around it and to understand when you know a little bit about it, can you still do some type of inference? Then this is the first bullet there that I like to put like the DNA that we have structural causal model. And then we are trying to do one side of the coin of what we are trying to understand about this model is it's a kind of fancy word now that's called explainability. We are trying to do some type of effect decomposition, effect identification, decompositions, bias analysis. Could be a fairness, that is a recent application that people is very interested on, and robust and generalizability of claims across changing conditions. Those are different tasks. There are books on top of this class of tasks. The other side of the structural causal model that we are interested in, or could be interested in, is this decision-making part. Maybe we don't care about understanding, or the first one is about what people like to say, opening nature's black box. We don't care about understanding. You care about, we are pragmatic, and you are just trying to optimize some measure. Then this is the decision-making part. One of them that is very close to us is the reinforcement learning part, but you can have in the science or in the biomedical science something called the randomized control trials. You can consider problems of personalized decision-making and so on. Again, there are books and many decision theories just on this top. Our perspective, quite simple, is that this is following, it's not a primitive, but it's following one of the sides of the coin, or what does a structural causal model means. For sure, you could have interaction about that. As much as understanding you have about the system, at least in general, this should buy some kind of mileage or to allow you to do more efficient decision-making. And when you are doing decision-making, this will be one of the comments or the notes in this talk, we are also learning about what is the underlying dynamics. This sounds very theoretical. For sure, you could or you should have applications. You could think about education software. Two types of applications that I usually have in mind. One is what nowadays is called data science, the intersection of computer science, of AI machine learning with the sciences or the empirical sciences. And we would like to try to give this label or stamp the label scientific for the inference that you have. You like to believe, or at least have some type of logic to say that we are being formal about that. And we have the side that I will be talking more today here, that is the AI machine learning, if you are like to try to design robust and adaptable systems. Today I will be focusing on the reinforcement learning part, that is our AI ML decision-making view that we say to sequential decision-making. Then if you are a postdoc or finishing your graduate studies, send me a message and you should talk. And you have some interest in these topics that I will not destroy at the end of this talk. That's it. Then let's go back to the talk, what I will be talking today. Let me make an outline here of the talk. The first part, I'd like to do a brief introduction of how I see what is reinforcement learning, and also introduction to causal inference. This will be the first, maybe 1/3 of the talk. Then I'll try to cast reinforcement learning through my causal lens, how I perceive it. And then I will talk about challenges, opportunities of when you see this as an integrated way, or in kind of encompassing way. What are the new challenges of opportunities, even if this exists? For sure, my comment here, I'll try to argue that it is the case that when you study these two sides, causality or reinforcement learning separately, we are losing something. There is something in the intersection that has value. Then that's the third part. The goal or the idea before people get unhappy, given that I'm UI is quite technical, I would like to try to introduce the main ideas, the principles, and what are the tasks that I care about. I will not focus on the implementation details or the nitty-gritty. My experience as a reviewer, a member of the community for some of these topics, we get very quickly in the details or not even understanding what we are trying to do. Then this will be my approach or my bias during the talk. For kind of more comprehensive discussion of the topics, as I said, this is a field report. This has been appearing since 2014. A quick note here about how I got here. I'm originally by background causal inference person. When I was finishing the PhD in around 14, I started thinking about, I usually make the joke that I was in causality land at UCLA around UW Pearl, and everything that we are doing in causality, it was good, and we were supported, and everyone was happy in our land. But then when you start going out and talking with other people, we realized people was not exactly as excited about some topics in the AI machine learning community, not so much in the sciences or more there, but in the AI machine learning, perhaps people are not so aligned with what we're doing there. And then I was thinking why this is the case, because I'm pretty confident, or at least in my gut, I believe that we are doing as a field, or in general, pretty nicely, or the results are amazing in some way. And then I start kind of digging or doing some introspection to understand why this was the case. And the answer was reinforcement learning. Reinforcement learning is, even though originally around 2014 was not acknowledged or no one knew about that, at least no one told me, the reinforcement learning is the way that we have in machine learning. It's a very limited way, but the way that you can have some type of causality. Now the question is, and then I start trying to answer, is it the case then whatever people did in causality for the last 20 or 30 years is completely useless? Possibly, because the folks in RL already solve it, or is there anything that is in this intersection that I'm referring? For sure, my answer is no, and then those are a few papers. Paper after paper will show that how when you are naive about these underlying mechanisms of that are in reality, how your RL agent could be terribly bad. And how can you then restore and put this together? And this is how I started. Pieces start appearing there. There's a new survey that is coming up in a few weeks. By the way, causal reinforcement learning, I call CRL. Then keep tuned that I'm trying to put that together, that is in the spirit in some way of this tutorial. Because the papers are more technical, very specific about problems. Then let me start talking about reinforcement learning. Everyone here is familiar. This is kind of textbook definition that is kind of goal-oriented mode of learning when you are trying to maximize some type of reward, usually numeric reward signal. You are learning about, from, and while interacting with an external environment. We have this notion of environment. And there's some kind of adaptation. You have adaptive learning, each action tailored for the evolving set of covariates or features, I should add. This is another word for, well, we use covariates because we're using causality, but in a machine learning, you use the word features, evolving set of features, and the action history of what you did in the past. There's some kind of interesting discussion that I really have when teaching, that is, this is kind of in contrast with the usual planning or type of programming that we have that you don't need to do learning. Then we are kind of do two things here. We are trying to plan at the same time, because we are acting there and you just don't want to explore all the time, but at the same time you are, you have to learn about the underlying dynamics. This is kind of another textbook definition that we have for the RL, just to get perspectives, that you have a parameter of the environment in the left side, where you have the agent and you have parameters theta, and then you observe some kind of state or context, and then this will generate some type of computation, and then you will do some action in this environment, and then you get the reward back. And this is, this is here, receive feedback from a set of in the form of rewards, agents, utilities defined by the reward function, and they must learn to act as to maximize the expected rewards. Now I want to add just one bit here that will make a whole difference for us. Instead of talking only about the parameters, I would like to add a pair here. I would like to model explicitly the environment as what we call a structural causal model. This is exactly what I said in the beginning in my add piece, that we have this we call SCM, structural causal model, that is a model of the environment. There are these mechanisms there, and usually this is tied with the G. Then there is a pair M that induces a causal graph G. I'll define a little bit better later, or causal graph or causal diagram I'll use interchangeably. We have this word action here. It's kind of overloaded. I would like to think that there are different types of interactions. I will talk more explicitly, but one is called observational, the other is experimental, and the other is counterfactual. I will define what action. Let's upgrade this notion for interaction. Then the two key observations that you pursue are kind of realized here is like the environment and the agent will be tied through this pair, SCM-M and causal graph G, number one. Number two, we define these different types of actions, as I just said, or interactions to avoid ambiguity. And I'll tell you how ambiguity or what this means in, I don't know, one or two minutes or three. Then this is my way of thinking about the RL, traditional RL, in a very simplified kind of 20,000 feet. Now let me do the same, or a little 10,000 feet from what a structural causal model means, or SCM. The approach that we take is following UDA Pro and many others that came for maybe hundreds of years. There's a lot of unification that happened in the last 20 or 30. And the idea that we take a process-based approach to these models. And the idea is that we have this reality decomposed in terms of this underlying mechanism. Here, for example, perhaps you are trying to understand some effect of the drug. You are an automated physician. You are hired by IBM Watson or some, perhaps I'm not sure I should say that in the video, but you are hired by some company to have some kind of automated system. And you are trying to determine the effect or some type of policy for the effect of a drug on headache. And then we see reality. What I mean by that, we have this reality that we have this variable that we want to analyze called drug. And drug is a function of this mechanism F sub D, where F sub D takes as argument the variable age. Depending on the age group, let's say, or the specific age, people will behave differently in terms of drugs. And U sub D. U sub D here means all the variables in the world that are generating variations for the variable drug that are not age. There's 1 million other variables that make up the decision of the person taking or not taking the pill. This is the U sub D. Note here, I'm just in the definition stage. I'm not saying how to get it, just saying these variables are out there. And then you have another mechanism related to the headache of the person who have headache or not. After taking the drug, that you have this mechanism assignment operator, F sub H, and then you have if the person took the drug or not, you have a different headache or not headache. If it's cured, essentially, depending on the age group, you have different behavior for the person if it's headache. And you have, again, U sub H, that is all variables in the universe that are generating variations for the variable headache that are not drug and age. And those are the two mechanisms that we care about. If you are God or the system designer, you do have this specific instantiation for this function. We are just a data scientist or AI fellow that is trying to understand about this massive phenomena. Then we will keep this guy unspecified. Causal, we use this expression called non-parametric. It's different than the usual Bayesian non-parametric, but the non-parametric here means that we don't want to say what is the form of this F. We don't want to say, we'd like to say, we don't know it. Then you leave it unspecified. Now, how we encode that, or given that we are leaving unspecified, that we don't know, you have our beloved causal graph or causal diagram. Note here that causal diagram means that you add an arrow from one variable to the other if the variable is an argument in the function of the corresponding variable in the left-hand side. For example, by the way, I put x, y, z here just to make my life easier, hopefully yours. But note that for the variable headache here that I'm calling y, the drug is an argument in the function f sub h. Then this means that we will add an arrow from drug that is x now, usually is the treatment of the decision, to y. Then the arrow has this meaning that it participates in the mechanism of the function, or the immediate mechanism, or the granularity that operates in the system. In this case, it's age, drug, and headache. You have another arrow from age to drug here, from z to x, given that age appears in the mechanism f sub d. And that's the meaning of the causal graph. Note here that when you move from the process side of the process view of the system to the causal way of thinking about the system, we explicitly, in some way, we don't even care, no longer care, even bothering about writing these f's. We, at least in this analysis here, and at least for today, we already gave up on that. It's too complicated phenomena to get the specific f's. Then you operate in the causal graph in which f is left unspecified. That's good. Now, process reality is running, and then we can kind of get what from there, what is real, it will be the data. People are very excited about the data, me as well. Now, the data gives us, at least in the abstract, some distribution. This is the distribution P of z, x, and y. It's called if you collect enough samples, we are able to recover this distribution. That's called the observational distribution, or the non-experimental distribution, or non-causal distribution. That's usually the distribution if you're doing classification or clustering, or one of usually of our tasks, you operate on top of this guy, this P. Now that's great, congratulations, but so far this is kind of very standard, and this is everything we could have been doing for a long time. You don't even need this guy, but why I'm drawing this way? Because we care about the effect of the interventions, or the causal effect of the drug and the outcome. And what's the causal effect? It's very related to this notion of intervention. When you go to this system that is in the left, you get this variable x with your hands, and you start moving the variable x. Then you can see how y will respond to the moves in x, regardless of any other variable that could be affecting the relationship between x and y. Note here that in the left side, the variable z, this third guy, is making x and y to move together. Then we call this confounding. It's confusing us. Now we don't care about that. We just want to know how x is making y to move, or y to change. The idea of intervention comes with this operator that was defined by Yuda, called the do operator, that essentially says that we'll go to this original system here, and we'll replace the f sub d, the natural way that people is taking the drug, by a constant. A constant, in this case, yes, the person will get the drug. There's no option. That's fixed. Then is the replacement operator that will overwrite the original mechanism or the original function by a constant in this case. You can play the game about replacing with other functions. We can discuss that. Here I just care about the primitive replacing by a constant. Now, for sure, if you do have the code of the system, you could do that directly. You don't need any sophisticated, no causal inference. You go there and change it. In reality, the drama or the challenge, or depending on how you take it, positively or not, we don't have these guys. This is just symbolic. This is just the meaning, the semantics. Now, for sure, you have the causal graph that is corresponding to this guy here, to this system here. The causal graph is, maybe you saw the mutilated graph, or the graph where you have the incoming arrows throughout the variable that you did the intervention cut, which means that this mechanism that was active here is no longer active. Now we have a constant yes that is the one that is giving the value to the variable x. This leads to a different distribution, a different animal in the zoo that is called the do distribution. If you are able to go reality and contrive reality that will match this guy here, you could sample from this process. This will give samples from this distribution list, that's P of Z and Y, given do X is equal to yes. Then this is called the interventional distribution or the causal distribution, among other names. Another name, for example, that you can get is a counterfactual distribution. Avoid use this name, but because I will need later. But usually you put, instead of having zy given do x, you can write as a subscript. Y sub x is equal to 1, or x is equal to yes, z sub, and so on. This is a possible notation counterfactual. Then don't get scared if you see that. This is just a different way of writing it. At least at this level of our analysis. Yes?
How do you control for use
What's that?
How do you control for use of the
I don't know exactly what control means at the moment. It's a not well-defined term. Then I may answer later, but let me leave it. Because we didn't define any control or...
I mean, the intervention. You just introduced intervention, and then you got rid of use of.
Oh, the quick notes here. The interventions in reality is a symbolic operator in which you go to the original system if you could, and then you replace the original mechanism with a constant. And I'm not saying how to get it, or I'm just saying that this is the operation because we are trying to convey, that was the insight in reality. You are trying to convey the idea that if you go by your own volition or of your own free will to this system, touch the variable x and start moving, this leads to this notion of causal and effect that we didn't have defined. Then this is just a definition here. I'm implicitly defining. There's the whole thing about how to get that in reality or in practice, but I will leave it, I will not get there. At least not now. But the second thing I forgot to mention, thanks for the question. Note that given that these U here are all these variables that we don't know, but are there, we even leave them just implicit in this model. There is no UD, UH explicitly encoded here, but depending on the part of the literature or the author, you may see the person adding the U sub X, the U sub Z, and the U sub Y here, or the corresponding U's after the relabeling. We just don't, and here, by the way, I'm assuming, I will not do that throughout as a common mistake, but here I'm assuming that it's Markovian in the sense that these U's are independent. I will not necessarily assume that in general. All the problems happen when it's not Markovian, but for Markovian case, we can just leave them implicit. Okay, that's good. Another names for these variables that the drug could be called the decision. The headache in this case is the outcome of interest, and the Z is the set of features. Now in the robot, this could be the location, where are you moving, and whatever you reach the position that you wanted to reach or the task that you are trying to accomplish. I'm very interested in robotics. If you're doing robotics, let me know. Then perhaps you can have examples that are more aligned with the specific setting that we are working. I think this is very nice for this setting. Okay, you have decision, outcome, and features. That's great. Now I'm just making this gray to show that, or to try to make it pictorial, that we don't have access to this guy, or you never measure this guy. The challenge that we observe, or as we say, we are seeing this phenomenon unfold in the left side, and our goal is to do inference about the phenomenon in the right side. Almost always, not in reinforcement learning, that I will tell soon, but almost always without doing the action in the environment. Note, we collected data in the left side. I'm just a robot, and I'm putting my hands in the back, and I'm just seeing reality unfold, and I'm getting these samples and registering and learning about this P of Z, X, and Y. No touch. Now we go, and in my mind, I want to say, if I go to this environment and start messing around or doing my interventions, what will be the effect of this intervention? This is this distribution here, PZY given to X. But I don't want to go there, do the intervention first, because I may be destroying the whole system, making a big mess. There's a friend here from economics. He cannot keep doing all the interventions all the time and see how the GDP, the gross product, will increase or decrease based on new taxation policy. There is some kind of analytical method to get the observational data that is already going on in reality and try to speculate about what would happen if he engaged in this new policy. The same with the robot. Robot shouldn't want to do a mass all the time. You have the data that's coming from vision. Vision, I mean, passively, you call. Then this is the dichotomy between the seeing and doing. Let me just define a little bit more formally the structural causal model slightly. Definition structural causal model M, or you can call data generating model, is a tuple with these 4 components that I already mentioned, the set V, the set U, the set F, and the set P of U, where the set V is the set of what we call endogenous, endo from inside, the set of observed variables V1, V2, Vn. Whatever in this case we have drug, headache, and age. This is V1, V2, and V3. We have the set of exogenous variables, exo from outside, or the variables that you decide to put outside the cut of what is your model of reality. This is the set of unobserved variables in our case. This could be U1, U2, and so on. In our case, this is the UD and UH. Those are the sets of variables that are there. Now you have for each of the endogenous variables Vi in V, you have a structural function, or a function, for simplicity, determine the value of V. Then for it, that is, Vi is a function f of I, or 2 sets of variables. One is, we call the parents. By the way, this is not a Bayes net. You ask at the end, what's the difference? I hope it will be clear soon. But you still use the family relationships. Then this is a parent, the parent set. That is a subset of the observable. Then there's the observed guys that are affecting the variable. In our case, in the case of headache, this was drug and age. That is the set of PAI. And you have another set of U, or UI, that is the set of unobserved parents of the variable VI. That are the hidden variables that are generating these variations. So far, I'm describing kind of a physical system without uncertainty. For sure, there is uncertainty and variability in the world that is not entirely modeled. Then you put outside the box, you kind of spread mass over this U's that leads to this P of U, the probability distribution over the exogenous variables. It turns out that this system admits axiomatic characterization. There is these 2 parallel works, one by Halpern and the others by Gauss and Pearl, given the axioms of systems like that. And whenever you're proving some theorems related to that, you are using some of these axioms. And it's kind of very nice and solid system. I just put it, there is some kind of solid foundations for that. And the result that we care about, or you care about here, is a theorem, quote unquote, that say that once you have a SCM M, this implies what Yuda call, I don't know if you're familiar with the Book of Y. Let me do a poll here. How many of you read the Book of Y in the room? Okay, maybe more than half. There's something that's called the ladder of causation. We usually call the causal hierarchy. Once you have a SCM well specified, this will induce a hierarchy of the different distributions. Let me show you what are the distributions that will play a key role in our understanding of CRL, of reinforcement learning. The first type of distribution is the one that I mentioned in the left side. That is the passive distribution that we call also associational distribution. Is related to the activity of seeing. If you read the book, sorry to bore you, I just repeat here. This is chapter 1 of the book, if my memory is right. You have the associational distribution. Symbolically, you write as this P of Y given X. The kind of questions that we want to answer is, how would seeing X change my belief about the variable Y? That's the seeing, and usually our inferences are here. All the machine learning, if you want, the counterpart in supervised and unsupervised learning are related to these inferences of this layer or this type. You have decision trees, Bayes nets, regression, neural nets, all they are kind of living there in some way. Now we have a second layer, or second type of distribution, that is the one that I showed in the right side in the previous slide. That's called the causal or the interventional distribution. Symbolically, the way that you write that is the P of Y given. Now you no longer observe X, but you are the one inducing the change and doing the do X is equal to small x, comma C, that is the set of covariates or context. It's related to actions or doing. What if I do X? What if I take the aspirin? Will my headache be cured? Okay, that's the do. This is very related to the topic today, that is in machine learning, the counterpart to what I mentioned before. This is the window that machine learning has to access this distribution. That is reinforcement learning, is related to the formalism that if you want, there is one called the causal Bayesian network. If you don't want to even take a full structural causal model, you can operate in the space of the causal Bayesian network that is one delta from our original Bayesian network, original mean from the 80s or early 90s, depending on how you define, I would say 80s. You have another layer of distributions that I'll talk more towards the end, that is called the counterfactual distribution, the full-blown counterfactuals. Is related to imagination or doing some type of retrospection or introspection. It's very related to the why questions that gives the title of the book. The type of symbolic way that you write that is P of y sub x given x prime and y prime. This is just one example in this language. What it means is suppose that the classic example, suppose that Joe took the drug that is x prime, and then Joe is dead, that is y prime. Now the question is, would Joe be alive, that is y, had he not taken the drug that is this x? Now I have this contrary to the factual world, because in the factual world, the guy did take the drug and he is dead. There is no dispute on that, I think. But now you ask this contrary to reality question, if he would be alive, had he not taken this route. Some people don't like so much these layers. There are kind of implications given it requires strong models. One of them is called the structural causal model. But still, it's pervasive part of human cognition and the notion of explanation. But I will live in between. I will live in between layer 2 and layer 3 in this talk. One thing that I didn't mention. If you get a structural causal model M, is an important other theorem. If you get a structural causal model M, it means that you can operate in layer, in other words, the guy that lives in layer 3, it means that you can operate syntactically in layer 3 and everything below it. Then you can operate in layer 3, layer 2, and layer 1. If you get a model that is layer 2, it means that you can operate in layer 2 and in layer 1, but you cannot operate or do reasoning or inference in layer 3. Then I will just go directly and take a full-blown approach and do layer 3 and be able to do all kinds of reasoning that you want. Now, I kind of valid any comment here, because I want to start connecting with RL, but this is my view, or kind of view, my view of, let's call my view of the field, of what's going on in causality and causality land. Yes?
Do you only reason like counterfactually and inferentially about actions? Do you like look at kind of dimensions of say the environment, or is it just actions?
I missed the beginning of the sentence, the question.
Do you only look at interventions or like counterfactual reasoning about the actions you take? So what if I take this action as opposed to what if I was operating in a different environment?
Yeah, if I understood, these quantities here are counterfactual quantity as well, and this one as well, if you want. As I said, we can operate, if you start from here, this one is essentially when this X is empty, you are living in some way in this layer 1. If the evidence of the factual world is empty, you are living in this do world. And the Y given do X, comma C, you can write, as I showed maybe 2 slides ago, as the Y sub X given C sub X. Then you can write in counterfactual notation. I just think it's useful to understand because those guys match some ways that we operate in the environment. Sometimes we are just doing the brute action. We are just going there and touching the variable X and changing it to see how Y will change. This is very tied with this guy. Sometimes we are just passive. Just let's see what's going on in the system. Then we are operating this layer. Sometimes I'm engaging in a deep thinking and saying, what will happen if I haven't woke up today, the VBAV will be unhappy, or what's with the cons? Then you can engage in this kind of speculative type of reasoning. Then this is more layer 3. Then I think it's useful to separate them. But as I said, if you are in this language, you can do all of them. And one more, and then I will move. I saw, okay. Anyone here? Now you can say, okay, Elias, great, but I'm in causality. What are you talking about? Can you be more explicit and tell how RL and causal inference fit in this picture? You talked in some way, but can you give me something more explicitly, I would say? Then let's start connecting and try to see how these guys are, what RL and what causal inference is trying to do in the context of decision making. The goal of both, or could be that we like to learn a policy pi such that we have this sequence of actions that it returns, let's call pi, returns x1, x2, and xn, that we are trying to maximize some reward. I write as this e sub pi of y given do x. Notation is tricky, but this pi here is the one that is giving the value to these variables x. Now, this is where I started around 2014. This is how the literature looked like. First, we have in RL the online type of learning, which agent performs the experiment herself, which means that the input of any analysis, like we do experiments when you go to this reality, you touch, you do the intervention in this variable, and you change and see how things go. Then this is why I'm writing experiments. I'm writing this do x, and you have in time. I is moving here, I from 1 to t, and then you collect these pairs here, do xi and yi. The goal of the analysis is invariably, or almost invariably, to learn about this p of y given do x distribution, or a function of this distribution. This is online learning. And I'll go one by one slowly soon. I'm just giving you the bird's eye view. Now I have a second mode of learning that people is very interested in now, but for many years that's called the off-policy learning. The agent wants to learn from the other agent's actions. You don't want to do the action, you want to learn from the other guy. The input here are, I move from experiments and I roll the word samples. We are not the one doing the experiment, then you just get data points. Samples, I call here, but you still keep the do here. You know that the other guy is doing the experiment. In other words, the guy is being, what I mean by that, the other guy is being deliberate about taking this action. Then you call this do x, and you still want to learn the y given do x. That's the off-policy learning. Now we have something that I'm calling do calculus learning, that the agents observed other agents acting. Difference, we don't know, or the agent doesn't know why the agent is acting the way that the other agent is acting. The agents could be moving without any deliberation, just in a kind of instinctive way, or non-subconscious way. The input of the analysis, now I have this difference between samples. This is still samples, but now I don't have the deliberation that the guy is taking the action for some reason, or randomize, as we usually do. If you're doing an epsilon greedy there, we're essentially randomize epsilon % of the time and getting a deterministic function, the other one minus epsilon. These are called deliberate. We know exactly how the actions are being picked. In reality, when someone is making the decision, in this case here, someone is making, with the economist friend, someone is making the decision about enrolling or not in the university. The guy is not playing probabilities here with the epsilon deciding to go to the university or not, and there are even reasons that he doesn't know. It's affecting him, perhaps the location that he is, or the peer pressure, or the family history. There are 20 variables that may be affecting the decision about the guy enrolling in higher education, the fellowship that he got, and so on. Then we call this non-deliberate. He's not doing an experiment. He's just acting and making the decision. Then this is this guy here. We have from samples to samples, but we have no longer the do here. You're just observing. This is the guy on the left side that you have in the very beginning, that you have left and right that's seeing. This is observing the guy at this level. The input of the analysis in the do calculus one mode, at least explicitly, is also a causal graph G. That is this description. The goal here of learning is to learn about the do x distribution as well. This is just pictorial in terms of the layers that we have. We don't care about anything, we just do the action. Go there and change the variable, regardless what's there. Here we are doing, someone already did the action, and you would like to know what if I will be doing the action, how can I use his data that is deliberate? And here we're just observing the guy to do the action, and you would like to do the action deliberate ourselves. Then formally, or if you want to a little bit more of syntax, this is the do itself, this is from a do to another do, and this is from the C to the do. Now let me go one by one here with a little bit more of details. Online learning, we like to find a guide that optimizes X star such that finding this X star is trivial once I'm moving here from P to E, but once the Y given to X is learned. The Y given to X can be estimated through randomized experiments, that is, or adaptive strategies such as the Epsilon greedy. If you have states, the MDP, the POMDPs are doing this kind of process. There's a randomization plus this deterministic policies that is deliberate. Then it's very easy to get the Y given to X, or this is the goal of the whole engagement in the exercise. The positive, the pro of taking this route is robust against these unobserved confounders, that is these U variables that was asked before about the controlling. This is robust against the U's. The U's may be there, but you're just going in reality and randomizing the variable X. Then I don't care about the U, because I am physically disconnecting the variable, the decision X from the U. Then this is the big win from this, or the big positive for this approach. The negative, that experiments can be expensive or impossible. In many domains, it's totally impossible to do a cancer, to effect of cancer, smoking on cancer. You cannot randomize or do experiment with human subjects. The effect of cholesterol in heart failure. It's not about ethics, but it's practically impossible to open the patient, throw a dice with 100 values of cholesterol levels and randomize the cholesterol. It's technically infeasible, and it's very costly, even when you don't have the ethical and the technical issue. Maybe, at least in the medical science, it costs $5–10 million, depending on the size of the trial, but to run a trial like that, it's really hard. Then this is the negative of this approach. This is the graphical picture, the way that I like to think. There is the world there in which you could have this U that you're asking about the controlling that may be affecting the decision X. We don't know why the guy is acting this way. Still, we just ignore whatever is going on in reality, and in a physical, hardware way, we implement this policy pi that is setting the value of X. Could be flipping the coin, or you can be even deterministic. Then this is called the post-randomizer, or the active world. And this is whole online learning literature. And this is just another picture that I like with the tapes, that we have no data from what happens before, and then we ignore this world, and then you start those kinds in here are the samples, and you start collecting data about the do X0, do X1, do X0, depending on where the coin, or where your policy is giving you, and at the end you are able to get this E of Y given do X. This picture, yeah. Now there is a huge discussion, a huge literature in covariate-specific causal effects. This model, what I just said, can be augmented to accommodate the set of observed covariates C, also known as context, depending on the literature. They use the set of the remaining unobserved confounders, or the UCs. Note here that instead of X and Y with the U, now I just add this C here that is affecting X and Y. This could be like the age, the ethnicity, socioeconomic status, and so on, the set of features that you observe. The goal is still to learn a policy, but now we have a policy that is parameterized by the C, pi C, so as to optimize based on the C, what we call C-specific causal effect, that is P of Y given to X, comma C. Huge challenge here, because when C is high dimensional, start getting hard to get samples from this distribution, even in the online way, even if you have the possibility of doing the intervention. Then a lot of work around that. The second family of methods that I mentioned is the off-policy learning. Y do X can be estimated through experiments conducted by other agents and different policies, remember? Positive about that is that no experiments need to be conducted. Then you don't need to touch the system or spend the money. The negative that is usually left implicit, these rely on two critical assumptions here. Number one, that, or I call A1, the same variables were randomized. You are able to touch and do the experiment in the same variable. This is called assumption A1. And the second one, the system of the agents see the environment in the same way. That is A2, context matches. In our case here, we just call the context is empty, then both are saying that they being affected and what is leading to their decision is the same. This is the graphical picture here. In the left side, we have a policy pi that is driving the first agent that decides the value of x, and then you wait time and you get this y. This is in time, right? Everything is indexed here by I. In reality, we like to do the inference about another policy, pi prime, that in this case, these two assumptions holds, that we are still, the scope of pi prime is still x, and is still affected by the context empty in this case. Then they match perfectly. There's a collection of methods called IPW, inverse probability weighting, that essentially we invert the probabilities of picking this action here, and you are able to speculate or to infer about this effect, about this other policy pi prime. But this is essentially what IPW is doing. There are like, I don't know, 1,000 papers doing exactly variations of that because it's hard in some statistical sense. But causally, this is what it is doing. This is the picture that I like. Same in the left side, you have the policy pi. You have agents that are already collected. This is full here, already collected many data points on the pi with this do x1. And you like, without collecting the data, this in the right side here, the yellow arrow is when you have the transition, that you like the agent. Here, agent doesn't want to do the experiment. Use this IPW, and then you can get what will be the effect as if you have done the experimentation. I just mentioned that. A lot of work here since the variance may blow up, given that we have divisions by guys that may be very small. And you can do clipping, and there are some ways around that, of at least how to think about that. This is the off policy. Let me tell you about the do calculus one that was not categorized before, at least until that. Our work, the y given to x can be estimated from non-experimental data. In the literature, we can get, this is called the natural or the behavioral regime or policy. The positive about that estimation is feasible even when the context is unknown and the experimental variables do not match. In other words, the off-policy assumptions that I just mentioned, A1 and A2, do not hold. Negative results are contingent in the model. You need a causal graph or some level of understanding about these mechanisms. For weak models, non-informative models, the effect may be not uniquely computable, or as you call, non-identifiable. This is here the passive world that we have in the left side, that is when you collected the data, and you like to have this do calculus type of inference and make a statement about y given to x, or about this world here in the right side, without doing it as well. Is off policy and the do calculus are in the same bucket, that we don't want to realize or to do the experiment. We want to be surgical about that. In this case, for example, if this is the model of reality in which you just have the action, the outcome, and there is some kind of confounder affecting both x and y, then this is a non-identifiable case. The do calculus will say that it is not possible to do this inference. If you want some kind of details about what this means, we have this survey with you that is at least in 16 minutes discussing the state of the art of this type of inference. This is, again, the picture that we have, same kind of tape picture. Here you have the data. The data is coming from this passively collected or non-experimental P of z, x, and y, observation, 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 so on. And then you would like to make the inference about this E of y given do x. There's just doing a piece of advertisement. There's a paper on Wednesday, that is our paper here, that we are trying to do. It's not phrased officially like that because it's a general task, but we are trying to do exactly this task. Instead of getting OBS, 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 and moving to the y given to x, here we can be getting the do z, OBS, do w, do whatever you want that is not the do x, and you like to infer about the do x. Then you can have a combination of the different types of experiments and observations to learn about the experiment over x. This is the summary here of what we have around 14. Online that we are essentially, online that we essentially have the world. We ignore what's there to implement your policy in a hardware or physical way. The second one is the of policy that we are moving from one do to another do, from pi to pi prime here. And you have these two critical assumptions about the same variables are randomized and the context C is the same, that is A2. And you have the do calculus that you have the C. You can generalize that, I just said, you come Wednesday, you will be welcome. But you have the C and then you like to move to the do without doing the experiment itself. Now, this is 14, then the valid question, or this was my question around that time, is like, do these strategies always work? It's beautiful. You are able to put under, I'm doing a kind of 20,000 view, you get the survey, but we are able to put under the same umbrella, understand causal inference and reinforcement learning. And they have these buckets, and there are like thousands of papers in each one because there are different types of models and assumptions that you can make. But still, that's good view. But do this always work? In other words, is learning in interactive systems essentially done? If so, by the way, for the first question, is it the case that AI is done? Like, don't need researchers. Why are we here? Despite the beauty of Israel, and we are very excited to be here. Thanks, Rina. But apart from that, what are we doing here? Do we need more engineering effort with whatever tech models and theory you have, and then you just developing the technology and just code? It's huge effort. You need a lot, but still, science is done. Let's move to the engineering part. Now, for sure, my answer, as I hinted in the beginning, I don't think so. But this was my concern, quote unquote. I was concerned to move to industry. It's partial joke, but not entirely, but perhaps we didn't have anything to do in 14. And I don't think it's true. Then I say this towards RL, causal RL, CRL. But I think it's a good point here to, given that we are talking about the past, and I like to start talking about the future. Any questions about the past or complaints from the RL person? Or or can I just keep? Yeah.
So in the previous slide, you showed the three models of learning. But isn't there an underlying assumption here that you're seeing enough samples of all, in all three, that you're seeing enough samples of all possible combinations?
Yeah, if I understood the question, yeah, there are some, at least in this picture here, I'm showing that as if you have the perfect sample in the left side for doing the Duke. The online, we are getting the samples on the go, and the game that is being played is how to optimize the samples. This is why we are not doing the Fisherian, the randomization from the 40s or before, that you're just flipping the coins and spending all your samples, and it's wasteful. This is why we have adaptive strategy. We are doing doing a little bit here and trying to optimize based on what's going on. Yeah, this is the game number one. Number two and number three, wherever the data is coming from, we do assume that the data, at least in this slide, that the data is perfect. And we still have the whole problems. There are, like, as I said, many, even when this holds. You are totally right. In reality, this is compounded. Now you have two problems of two nature that comes together. One is the inference that is if you have the perfect data, but now we don't even have the perfect data. In other words, every P probability that I put here, in reality, I have the P hat, or some approximation to this P. What's that?
Maybe even not all possible actions, but taken in all possible states of the world.
Right. That's right. And when you have some types of a little bit the violation of the action, meaning you collect the data from one action and you move to another, I'll talk about that. And I think this is a main one. Is a main one that we like to handle. And handle, I mean, try to be systematic and as formal as we can. Because we are already trying to solve these problems in many different ways. Thanks for the question. Yeah, speak loudly, please. Observational what?
Normal supervised learning, for example, is it just the fact that you specify the causal graphical model? It's not clear to me how do calculus line is different from supervised learning.
Yeah, that's a good one. Perhaps I would like to invite myself next year. I'll come to UAI, give another tutorial. Because I went very fast. I spent maybe I don't know, 1 month discussing this kind of question. Look, let's go back a few slides. That's a good question. That's picture that I want you to have in mind. Let me put the yellow here because it's nice. Whenever we are doing the type of supervised, even unsupervised, focus and supervise, learning will operate in this left side, which means that we have data, or for sure it can be finite samples as alluded here in the previous question, but we have data that is coming from this process or from this distribution, P of Z, X, and Y. We have this hat. And now we are trying to do some type of inference about the P of Y given X of the distribution. Classifier can be taken this probabilistic way. I want to infer the outcome Y or the label given that we have this X that is this set of features. And this is supervised learning. A way of thinking about supervised learning. For sure, you can have a 1 million model to do this kind of things, but it's still, you're computing some kind of Y give P of Y or expected value of Y given X. Now here I'm talking about a completely different animal because the data that we have comes from the left side, but we are trying to do the inference about the distribution in the right side, right-hand side, that we have 0 data points. Oh, yeah, that's fair. I'm just telling you that there is such a mechanism, but I'm not telling you how to do it. I'm saying there is this thing called the do calculus, chapter 3 of causality book, Pearl 2000, chapter 3 and 4 if you want, but that tells us about how to move from the left side to the right side. I'm not giving the details. I could spend 1 hour. And I apologize for that. Perfect, yeah. No, that's right. And this is one of that's perfect. And I added that in this learning, where is it? This is this guy here. That, yeah, as input of the analysis that the do calculus learning, we assume that we have this G. That is already the summarization of this mechanism. This will be what buys us some mileage to be able to hope to move from the left side to the right, from the observational to the experimental. And I also added that the negative here is like if your model is weak, if you know too little about the system, then we get this answer saying, I cannot do it. The calculus say, not I cannot do it, impossible. Ilya is here. He was the first to prove something like that. Then it is provably impossible to do some of this stuff. But yeah. What we are trying, if you are interested in this one, we are trying to relax some of these assumptions. And instead of assuming that we have the causal graph, what if you are having something that comes also from the data that we call equivalence class of graphs, collection of graphs. Our UAI 18 is exactly this paper. Anyhow, and a lot of work in the field of, just to move on, but there are a lot of the work in the field of causal inference is exactly to understand under what conditions can you do this type of inference. One thing that I didn't mention, that causal inference is pretty good, or I would say a set of techniques that is pretty good about when you have some type of qualitative knowledge about the whatever phenomena you're analyzing, how much information you can extract from that. This is causal, about this manipulation of qualitative knowledge to translate to quantitative. Reinforcement learning, on the other hand, is pretty good about how to efficiently collect the data. And the models are quite weak. If you get essentially any prototypical model like a Bandit or MDP, this is a very weak, non-descriptive type of model, because everything, all the heavy lifting is in the data collection side of efficient sample collection. Anyhow, this is a good note as well. Any other question here? I have 1 more minute to move to the second part. Hopefully you're alive. Yes, David.
I'll just speak loudly. So a lot of reinforcement learning deals with very large state spaces. And those large state spaces imply a kind of contextual nature to reasoning, which implies to me context-specific independence, which Bayes nets are often not good about reasoning about. So how can we deal with that kind of contextuality of action?
Yeah, that's a hard question in some way because there are many layers. The way that I like to think that we have this kind of huge state space is that we are trying to keep this causal graph that it is there implicit in the system. We are trying, meaning, not that someone said, not that Rich Sutton, I talked with him, but not that he said 20 years ago, let's keep the causal graph implicit. Didn't happen. But I think that's the idea, that whatever, if I'm clever enough about representing this S, and this is what the deep reinforcement learning is amazing today, because we're able to kind of reduce the dimensionality of the problem in a very massive and efficient way, then we're kind of avoiding to model that. Then it's, and more broadly, the context specific, or the context specific that you are referring could be even considered the graphical structure itself that is turning on and off the arrows. As I will show, hopefully I'll show, if I'm efficient enough with my time, there's no way of keeping the graph implicit all the time. Meaning, this is the point, this is why I say CRL, and I try to contrast with the textbook picture of the RL, that you don't, the graph is there regardless of I liking or wanting or not, because the mechanisms are in reality. The question is like, are we making them explicit or not? Now, the question is like, do we have the option of making them explicit or not, or this will hurt us in some way if you leave them implicit? I don't know if I answered it because it's, yeah. Did I answer the question? Or in some way? Okay. Okay, guys, let me move here. Then going to Causal RL, I would say challenge of opportunities, I would like to talk about, based on my time management here, about 4 different types of tasks. The first one is what I like to call generalized policy learning. That is we assume that the world is like this cookie cutter way and match these 3 modalities, online, offline, and the do calculus learning, and everything will work in these buckets. Reality is quite messier, and usually you get a lot of negative answers, instances that I will show. Now, what I'm calling generalized of policy is like, let's try to have a mode that is integrated these different modalities of learning, trying to mix the positives and kind of attenuate the negatives of each one. The second one, we also assumed, without noticing, that whenever you say that I like a policy pi and the action variables are x, that I already know that I want to intervene in this variable x. Reality sometimes is better just, this is what I call n. Sometimes you just let the system evolve naturally because it's already going to some good place, and the best thing is not to touch it. Then the better thing sometimes is to say, I just want to keep in my place and let the system evolve, no intervention. So far we haven't contemplated that. Still, if it is the case that you decide to do the intervention, why do you intervene in the variable x? Perhaps there is another variable w that will be the good target to do the intervention. Possibly, I'll show examples of what this means. Then they are called it when and where to intervene, another class of tasks that are in this between. The third one is the one called the counterfactual decision making. So far, we assume that we have this kind of automata behavior, that we have the do calculus, do kind of behavior, that something in the context of the sensory inputs comes in, there is some process, and I use this policy, I will do this kind of do policy. I will do some kind of randomization or some kind of deterministic policy. The agent never stops itself and say, I'm operating in this way, but I should be doing differently. Pretty much in the spirit of layer 3, the one that I like to call counterfactual, y sub x given x prime and y prime. Then given that we have these repeated kind of interactions, we could consider to do not a do type of intervention, but a counterfactual type of intervention. Then it's very related to the idea of intentionality that's loaded here in the context of AI, but intentionality, regret, another one that is overloaded, and free will. Let's see if I can get there. And there is another one that is where I started, or many years ago, maybe 10, where I start thinking about some of these issues. That's about the robustness and generalizability of causal claims, what I called at the time the transportability problem. Here we assume again that the agent is one environment and is collecting data and trying to do inference in the same environment. Now the question is, we move the agent to another environment. We don't want to start learning from scratch. In some way, we like to leverage what's called the structural invariances, or what are the commonalities across these environments, to do the inference without needing all these experiments. And this is called transportability. Though this is references for the papers, and by the way, we are not done. One of the reasons that I'm doing the tutorial is like we need help all over the place. I think this is the beginning. Then I'm just giving the flavor and my field report about what I think it should be the CRL. It's pretty much open and help needed. Despite the progress, I think we did good progress as well. Let me start talking a little bit about this generalized of policy. This is with my student, Justin Zhang. The idea is like we have an online learning that is usually undesirable due to these financial, technical, or ethical constraints that we have. In general, one wants to leverage data collected under different conditions to speed up learning without having to learn from scratch. This is the online part. On the other hand, the assumptions required by the off-policy and the do calculus learning are not always satisfied, not always met in many real-world scenarios, mainly due to these UCs, unobserved confounders. They are all over the place. In other words, there is the system that is moving some way. We don't know why they are doing whatever they are doing. Then many of these kind of idealized settings, the assumptions in these idealized settings may be violated. In this task called GPL, we move towards realistic learning scenarios where the three modalities come together, including when these most traditional assumptions are violated. Let me give you an example what this means. Simplest possible setting that is from this Ichikai paper in 2017. Task of, suppose that in robotics, suppose that you're learning by, it's called learning by demonstration, when the teacher can observe a richer context than the students. For example, the teacher may have more accurate sensors. Have a robot that has an infrared eye and the other robot that is observing it doesn't have infrared and doesn't know that. Then you have this, you have this mismatch of the assumption A1 that they have access to the same context C. You already don't have that. The second example is like what's called optimal experimental design from observational data. That is the example that I use. Syntactically, we are moving from the left, this is the first slide, from the left side observational to the experimental. Then as input, you have the distribution P of X and Y, and we would like to learn about the distribution P of Y given do X. Suppose that you have a physician that is making these decisions X and Y, and there is this all set of covariates U that is unobserved that is making the physician to act in the way that is acting, perhaps how the person is balancing, the type of the skin, the tone of the voice, and so on. Physician is analyzing that, even in the subconscious level, until it decides what is this U, until it decides what action X it will pick. And then that's great, and you can have tons of data of this kind, that is the P of X and Y. In reality, we like to know, not about to do a prediction, but we would like to know what is the effect of this drug in the outcome. Why? Because the physician may be giving the drug for the guys that will be recovering anyways. Maybe the socioeconomic status of the person, the guys are giving the drug for the people that have high SES, socioeconomic status of the family, and they have maybe better hygiene or better food or better type of environmental conditions that they will be recovering and getting this Y in a high value. Let's say the Y is the quality of life or a number of years that we live. And they are not giving the drug to people that is poor that will be dying. When you get the data from this side here, the right in this case, and you see it seems that the drug is amazing. In reality, the drug is not helping at all. It's just the way that the physician is giving the drug is biasing, and it seems that the drug looks good. Then this is why you have the FDA, for example, the Federal Drug Administration, the American FDA, I don't remember the name, I don't know the name in Israel, but that will actually get this P of Y given to X. Again, the assumptions, if you run the do calculus, as I mentioned earlier, do calculus will say not possible to run. Because we have this latent variable here, you can show that it is impossible to make a statement about the Y given to X distribution. If you try to do the off-policy learning, off-policy, I said A1, but the assumption A2, that they have the same context, is violated. Because one guy, one type of agent that this physician is able to observe the U, this is affecting their decision, while the other agent, this is not happening. The other agent just wants the causal effect. Now, A1 is matching in this case, but that is, they are considering the same variable X, do X, do X. Now what we can do is the following. Let's just pretend, let's ignore that this difference may be a problem and pretend the physician and the FDA is overloaded again, but are exchangeable. And let's call this the naive Thompson sampling. That is the allocation procedure, a way of giving the drug to some people. And then we can have the plot here. This is the kind of plot that we have. That is the number of interactions in the system, that is in the x-axis, and the y-axis is the cumulative regret. That is an oracle, someone that knows how to give the drug, minus whatever you are doing. And this is the naive Thompson sampling that you get here. Just pretend that they are the same. In other words, you get the observational data P of yx, and we'll put that as the prior distribution of this, the Thompson sampling or the TS solver. Now, let's plot here now. Let's throw away all the data and plot the naive Thompson sampling operating without the data, the standard one, the vanilla. Then this is what we get. This is a much better behavior. Maybe after around 2,000 interactions of experiments with 2,000 units, you'll already be able to know what is the best drug. Then the question like, how could this be happening? Could more data be hurting? This seems kind of to defy our deepest and strongest conviction. This is like, data is always good. Give me more and we'll give a party. This is not happening here. Let's do the following. Let's open up what's going. Let's plot some kind of 95% confidence interval. What's going on inside the solver, inside of each of these lines. Note here the following, because I know the ground truth. Given that this is the simulator, you have this y given. Let's start from the truth. This is truth. The y given do x0. That is the guy in the solid arrow, is higher than the do of x1, y given do x1. X0 is better than the x1. On the other hand, the data that we get from the physician is that the y given x1 is larger than y given x0, which is flipped. And this is the data that we use to seed or to put as a prior our Thompson sampling procedure. Then this is the behavior that we have. In the left line, you have the solid line that is this guy here, y given x0, below the y given x1. And then this keeps going forever. For sure, depends on how you're setting the weight of these priors, but this is with a small number of samples. I don't remember now, maybe 1,000. This is the vanilla one, the one in blue, that we start kind of half and half between the x0 and x1. And after, very quickly, maybe after 100 interactions or even less, we already, and this is the CI 95, we are able to distinguish and realize that the x1, the x0 is larger than the x1. Then the question for sure is, can you do better once we know that this is happening? But before that, let me just make a point about the size of this prior, because this is the data. This is, let's say that I'm correct, by the way, I don't know the number, but let's say that it's 1,000 samples, I don't remember. Now let's make the size of the prior smaller. This is like 20, 200, 250, 200, 100. The blue one is 0 samples. 0 is amazing. Whenever you have 100, we start being able to recover. If you go to the sample 105, 150, it's still possible. 200, start getting hard. 250, we're already a little bit messed up. 1,000, we're completely messed up. The thing is trapped here in some way. Now, which is the against, is everything that we don't want. Because our goal is that this number here should be huge. Because we do have tons of data that is observation from the hospital, from the physician, or from the other robot that you can see interacting in the system. And you like this data to be playing in our favor. Here the data is hurting us. The best thing seems to be not to use the data. I'll not go over the numbers. I'll make these slides available to Vibhav. But we can see the numbers about, this is the true SCM on the high layer, the parameterization of what could be the simulator of following this system here, this simplest possible causal model that you have the decision X, the outcome Y, and there is this one hidden variable U that is affecting both X and Y. And then you have the probability, whatever, the correct parameterization of the system, the P of U, and the functions. And this is kind of the behavior that we got in the simulator, that we have Y given X, in which X1 is larger than X0, in the second column, or the third here, and in which Y given do X0 is larger than do X1. Now the questions that I ask, I think implicitly here, but or maybe in a cumbersome way, but does this imply that we should throw the data that is not collected by the agent away and start learning from scratch? That's an obvious question here. The answer is hopefully not, because this goes against any intuition that we have about learning. But it does demonstrate that in very trivial violation of the setting, when they already don't match in such a, there is just one variable here that is generating variations for one guy, that is this U for X, is not happening with the other, we already completely messed up. Then, but the answer, the first is hopefully not. The second question is, how do we know that this pattern is appearing? Someone could say, this is an exotic pattern. Whatever you crafted here as our example, you may go home and say, oh, it's true. He was telling me the truth. That's a parameterization that leads to these numbers. This is observed, this is hidden. But it can happen. But you see, this is just a pattern that you are crafting by hand. But the question, like, how do we know that this is not happening in our data? We spend 5 years collecting. If you play with people that is data, it's a struggle even to get the data. But they spend 5 years collecting the data. How do you know that this is not here? I know because I'm the simulator guy. I'm the one that have the code. The question is how to do it, how to know that. We usually don't know, which seems to suggest that you just throw away the data. Then after all, the question is like, is there any useful information in the observational data? In this data that has this bias that you show that the behaviors kind of deteriorate, is there anything good there? Or can you just throw away with confidence? And the answer is like, yes, there is useful information there, for sure. The world will be terrible, and you will be learning all the time. And the intuition. I may be not exactly like Rina. We are seeing the system in different ways, but I can observe her operating the system, and I can learn something. Maybe not perfect for me and not exchangeable, or in a Boolean way. And then the question how this could happen. This is this task one. there's two steps to the approach. As I said, I'll just give you the big picture here. The first thing, we'll try to extract the useful information from X and Y. We are not pretend, I use is loaded. I will not naively assume that they are exchangeable. Can I get Y given, probability of Y given X is equal to probability of Y given to X, but let's try to bound the Y given to X in some way. We can use results. There is a result even before this 96 in URI 94. There is work by Balke and Pearl how to do that. In some cases, very hard to generalize. We can do now in difficult models. We can do that in these models is discrete. We can do in continuous and so on. But that's the first step. Let's try to do bounds through the constraints that we have about the system. You can show how the bounds look like, and you can show that the bounds are tight. Tight means that you extracted as information theoretical side. This means that you can prove that you extract as much information as you could from the observational distribution that could be useful to the interventional one. The second step is how to use this information now in your Thompson sampling, in your allocation procedure. Essentially, you take this as input as well of the Thompson sampling. I'm not going all the details, but essentially you do some type of rejection sample, given that we do have the bounds, and you know where in other words, you know where the value of the effect is. You can avoid B-sampling, or you can reject each sample that we get that is outside, lies outside this range. This is Thompson sampling. You can be, which is quite nice and works in practice. You can do that in UCB in some way and be able to prove. The nice thing that you can prove that the convergence of this algorithm will be much order of magnitude faster than the usual one when you don't use the observational data. That's kind of amazing result. Let me show just the plot of what this means. The winner so far between the red and the blue was the blue, but now you could have the green one in which we are using this approach that I alluded here about that we are able to kind of chop some of the variance that you have. The game that is being played here is how fast can you get convergence or not lose convergence. In the red one, it seems that you are even not converging. Here you can kind of chop some of the area, and this is kind of the line of the regret versus the number of interactions that you have in the causal after maybe 100 samples. In other words, instead of doing an experiment with 1,000 people and spend, I don't know, $5 million, perhaps you can do an experiment with 100 people and get the same confidence in the result just using the data that is already sitting there in the hospital. In the case in the medical setting. Robotic setting, I think, is very compelling as well. This is the reference that we have about how to show that in this specific setting. Bandit. We can generalize that. This is task that I said that is moving from this graph here when you have this mismatch that you are learning from demonstration, when there is a mismatch between the sensors of the two types of agents. Now you can have another type of violation that is the one alluded here earlier today, that when they don't match, the action space is not the same. The variables that you are intervening. For example, here you can do the intervention on this variable z. Perhaps you have a robot that is a very old model that is able to touch this variable z with these actuators, and z affects the variable x that then affects the variable y. This is the old 1.0 version of the robot in the left side. But now we have a new generation of robots coming out that's 2.0, that the guy has much more surgical or detailed kind of way of actuators that he is able to touch directly in the variable x that is much closer to y. Now the question from this, 10 years of deployment that we have in the robots to Z can use this data to calibrate and start to have a policy to the new generation of robots that is do X. And that's kind of same flavor of the question in this generalized policy learning. And you can have the other way around, that you have a robot that is very efficient, and perhaps now the robot, someone take a shot in the robot or destroy the robot. Now the robot is just able to operate in the do-Z way. It's kind of impaired. Now can you use the data that the robot has for 10 years that he was able to move happily and fully to this new situation. How to do that. if you go on analysis one by one, this is the violation. Do calculus, you say no in this case. This is even our UAI paper 12. And do calculus, you say no in this case. Of policy A1 is violated in both, that they need to match the same action space. And here we have do X to do Z or do Z to do X. That is a no-no. Then it doesn't fit the 3 buckets that we have before. How to do that? That's the question. This is the picture here about the generalized one that we have. That we have a mismatch in terms of the policy. That here you have a context C. That is the data is collected over do X, comma C, and you would like to do an inference over the do X in the, without having access to the C. We need to have some kind of bounding and allocation procedure that takes this into account. This is step 1. Step 2, can you prove that this will generate to provably guaranteed ways of improvement. Let me skip the algorithm for now, because I want to talk about other things. For sure, you can do that in other models that is not banded. First, we showed banded. Now you can do contextual banded, for example, that we have this C here. All these variables here that we have the dashed lines, it means that now we no longer assume that there is no unobserved confounding here. There is this latent variable that is affecting both C and X in one setting, another one that is affecting C and Y, another one that is affecting X and Y. Then there is this UC all over the place. Then this is the contextual. And you can show the results are good. And you can prove as well. And there's another one that I like a lot. This is a recent one, still not public, but I can talk, I guess, here, given the UAI friends. The one that's called dynamic treatment regimes, that you have this kind of sequential, it's called DTR, the sequential nature that you are taking actions X1, X2 in time. You come back next month to the doctor, and the doctor decides to give different treatment based on the treatment in the previous months, again, assuming that you have these UCs. Okay, this is task 1, that is the generalized of policy. This is this mix between the on policy, off policy, and the do calculus type of learning. Now I would like to talk about the when and where to do the intervention. This is work with my postdoc. It's called Sangak Lee. By and large, it's assumed throughout the literature a policy space such that the actions are fixed a priori. For example, we already know as a designer of the system that this X is whatever X we have, and we are not changing that. And also we assume that intervene is a good thing. Let me read it. Intervene is usually assumed to lead to positive outcomes. That is good. In this task, our goal is to understand under what conditions interventions are really required. As I said, sometimes it will not be. And whenever this is the case, it's still unclear what should be changed or manipulated in the underlying causal system, such as to bring the corresponding or the desired state of affairs that we have. Let me give you an example. This is the standard bandit model that you have action X, outcome Y, and then you fix this policy pi that I'm not showing here, just for clean, to be cleaner, and that decides the value of X, and then you have your kind of average over in this U. U is no longer affecting. Now, assume that we are not a priori committed to intervene on a specific variable, but just want to optimize this variable Y. For example, keep the variable Y in a high value. This is the health of the system, or the health of the patient, or the happiness, and so on. And let's add one observed and one unobserved variable in the system. Just one small variation. 2 variables, one observed, another unobserved. Then from the standard bandit case, we are adding meaning there is now the link from U that is also affecting X. And there is this variable Z here that was added, this observed added that is affecting X. Now I have this little model. And the question, like, in terms of when and where to intervene, is like, what are the possible things? Maybe the case is like, I don't want to, we want to optimize Y. We want to keep Y in a high value. And now we have the 4 levers. In reality, we can intervene on Z, you can intervene on X, or you can do X, you can do Z, or you can do X and Z, or you can do empty. Just let the system evolve by itself. The causal insensitive, this is very psychological, very emotional. Causal insensitive strategy, just joke. Causal insensitive strategies, let's ignore the causal structure, as I think we alluded to David. Let's ignore the causal structure, take X and Z as one large variable, and search for the guy that maximizes this E, Y of do X, comma, Z. In other words, what we are doing in reality is assuming this model here. This is the model in the agent's mind, that we have X and Z pointing to Y, and the U that is the source of randomness parent to Y. This is the causal model that's assumed. The true causal model is this one. But if I want to be insensitive relative to the causal dimension, I'll just go for this guy on the top right. Now I want to show you, I want to show you that this is not good, not necessarily good. Before that, let me make just one more note. This is nice. There is one strong intuition as well in decisions, at least my intuition at the point, maybe 15 or 16, that is like, if I want to optimize the variable y, the best thing to do is let's go to the guy that is closer to y. Who is closer to y? In this case, x. Let me get closer to y such that I have more controllability over y. If I get to a guy that is very far from y, like in this case z, but could be 10 z's before it, perhaps the effect will get diluted. I'll go to the womb of the mom and I'll do an intervention there. It will take 16 years or 20 years until the guy goes and decides if they enroll in higher education. Then how can an intervention in the womb have this effect? Then let me go to the closer that we have 1 millisecond before he is deciding. I'll tell him, I'll give you a fellowship. And then I'll have a higher effect. A strong intuition that I was buying in. Then it seems to be good. And in other words, this thing that I will be causal insensitive, and I will do X, do Z. I will not show here, but you can see through the do calculus that Y given do X, comma, do Z is equal to Y given do X. Because there is no link from Z to Y that is passing outside X, not passing through X. Then P of Y given do X, comma, do Z is equal to P of Y given do X. Then it seems to match. I can be insensitive and I will still be aligned with this strong intuition that is better to get closer to Y. Now I want to show that this was not the case. This came up when I was visiting Alberta, the reinforcement learning group there, that I was on the field trying to learn from how RL people are thinking. And this is still mission. I'm trying to understand. If you're RL, talk with me, that I would love to. It has been a long journey, but very good. Rewarding, I should say. But let me show you the example. This is the thing. Now this is the parameterization that you have. Suppose that is unobserved by us, by the designer of the system, but nature operates in this way. You have z that is equal to some variable u. There's a typo here, uz, let's call, some source of randomness. X, each variable will be an XOR of the parents. Then x is an XOR of z and u, and y is an XOR of x and u. And now this p of u here is half and half, is a fair coin. Now, what we're trying to show is, or what we can see, this is the observation, I say, y given to x z is equal to y given to x comma z for any value of x and z. And this turns out to be equal to 0.5. Just, we can see that fast, don't need to do a lot of algebra. The z doesn't matter, you are just replacing, recall, this is a replacement operator. Instead of x following z, x or u, you just set in the value of x is equal to 1, for example. Now, the value of y to be a high value, that is 1 in this case, you're just playing binary here. E of y equal to 1 given do x is equal to 1 is probability half, because if u is equal to 0, because we have 1 plus 0. If u is equal to 1, you get 0. Then, and you can do the other assignments. And you see that regardless of the value, this is 0.5. Then to keep y is equal to 1, you can keep that fraction of time of half of the time you can keep y at this level, in a high level. What about z? What about if you do the intervention on z? Y given to z is equal to z, let's replace here, z and u we replace here, then I have y is equal to z or u plus u, that is z. Then the e of y is equal to 1, given do z is equal to z. Then, given that we are doing the intervention of z, if you are able to set z equal to 1, you are able to keep all the time y is equal to 1, which is higher than the do x counterpart. Then this first example that I found that do z equal to 1 is optimal. Then it defies this very strong intuition of getting closer, which opens up the problem. This came from the Alberta conversation. It took 2 years until we have the paper. This paper appeared in NIPS last year, in the RIPS last year in 18, on how to do that systematically. In other words, you can get any causal graph, and how do you know what are these variables that could lead to the highest possible outcome of the variable y? This is just a plot. Oh, the plot here is about the do z policy, that is the kind of oracle one, that is the red, versus this naive policy, insensitive to causality, that we call all at once, that we essentially have the do x, comma, z, comma, whatever variables you tell the RL guy that this is manipulable or is a lever in reality, you can do the manipulation or the intervention, and they are just kind of checking what's the value that will lead to the highest outcome, possible outcome. This kind of combinatorial approach. The combinatorial one will never converge because you don't pick the do z. It turns out that we can have something in between. That is the answer that I get more commonly. They say, oh, let's just try all sets. I can try x, I can try z, not only all values, but let's say all values of all possible subsets of the variables that are manipulable. Then these will eventually converge, is the green guy, but it's kind of obviously totally impossible in very small instances. And it's kind of, whatever, it's kind of stupid in some way. The question, can you do better than the naive approach? I will not define it. This is just showing, let me move here. I have more half an hour, right? 25. And then what we'll do in the paper, just to give you a, we start trying to derive properties of these graphs, of the causal graphs, try to understand what happened in this example, in this baby example here, why, in this case, by the way, the z and the x are the two contenders. If you try x and z, for sure it will not lead to something good. There is some property that you can derive that you say that do x and z is bad, or it never lead to the good thing. Then the contenders here is do x and do z, and we do need to do an intervention in this case. The empty set cannot lead to the highest possible outcome. Then what are the properties? I will leave to you to have fun. In this case, the do z is the good guy. Do z can lead to the highest possible outcome of y, or the no intervention. The do x cannot lead to the highest possible value. I overestimated my time management. Okay. Now, I would like to talk about this counterfactual decision making. This is with you, the pro, and Andrew Forney, that was a student in the group. Agents act in a reflective manner without considering the reasons or the causes for behaving in a particular way. Whenever this is the case, they can be exploited without never realizing and exploiting forever. You can kind of impinge infinite loss in these agents. This is a general phenomenon in online learning. Whenever the agent optimizes based on the Fisherian kind of randomization or the do distribution, that is the do-like, which includes all reinforcement learning settings, this may be happening. Our goal here is to endow agents with the capability of performing counterfactual reasoning in the layer 3 type of, in the layer 3 sense, taking their own intent into account, which leads to a more refined notion of regret and a new optimization function. In other words, we're saying that all the RL or the causal setting that you are trying to optimize based on the layer 2 or the do distribution, the E of y given do x, everything is around trying to optimize this guy. You're saying, no, don't optimize this function. There is another function that is based on a counterfactual, that is this y sub x given something else that should be the guy that we optimize. That's our point there, the main point. Let's see what this means. I'm assessing here my time. Okay. Question, this can be rephrased as how should one select a treatment X star to a particular situation or context U is equal to U unobserved so as to maximize the Y. This happens in robotics and medical and economics and so on. Let me give you the example that shows this very clearly, that shows the tension between doing the do. But one thing that I didn't mention, just realize, the do is a population level quantity. You usually talk about the average expected reward, average expected ROI, given that we are doing this X. In this counterfactual is much closer to what could be called individual level or unit level causality. I'll try to convey what this means, but the tension between individual and population level. The goal here would be to find a strategy pi so as to minimize the cumulative reward, cumulative regret, could flip. The setting is the following. This happens, I have the idea when we are in the NIPS in the casino. I think it was Lake Tahoe, around that. It's a little bit depressed. Then you have this thing called the greedy casino. Greedy casino has two types of machine that we call X, type of machine X0 and type of machine X1. Then you have the reward Y that will be binary here, that you are winning Y1 or losing Y0. Now we have something that we don't know it's important, but it is, that is the blinking of the machine, or the blinkiness of the machine. The machine may be blinking and making noise that we call this variable B. Could be B0 or B1. And you also have the drunkenness level, or socially, then you have the drunkenness level of the person, that this can be D0 and D1. And this is the causal graph of the setting that you have there, that you have decision X, what is the machine that you are playing. Now we have the BD, that is unobserved confounder. We don't know that blinkiness and drunkenness are playing any role. And you have the variable Y, that is person is winning or not. Now there is a regulation there in Nevada saying that, these I'm making up, the numbers are different, and you check the regulation, but this is the story in the paper, by the way. This is our paper, NeurIPS 15. There is a regulation saying that the payout, average payout has to be greater or equal than 0.3. The casino cannot be too greedy. Now the casino hires a team of psychologists, anthropologists, and people that understand human beings, and learns that how customers operate and decides in the casino floor. And it learns, let me not show this one, that is kind of scary to me. The casino learns how they operate, and the main idea is like, if the person is drunk and the machine is blinking, they are attracted to the machine with a higher likelihood. If the person is not drunk and the machine is not blinking, they are attracted to this type of machine with higher likelihood. Then people that is drunk will be more likely to be attracted to this type of blinking and noise and effusive kind of machine. And not drunk, you are kind of more shy, and you are avoiding to call attention to yourself. That's the behavior that they go for. They spend a few $1,000,000 and they pay these psychologists, anthropologists, and cognitive science, and this is what they learn from the study. Then casino is trying to exploit that. Then this was the lesson, and then they decide to do the following. They hire someone in NIPS and UAI and ICML, someone that's a computer vision person. And now they install, that's not part of the numbers, but they install in the machines a camera that will take a picture of the face of the customer and will detect the dilation of the pupil, and they know if the person is drunk or not. Then they will set up the payout structure in this way that will penalize the people that is going for this type of machine under the drunken condition and the blinking condition, and also penalize the person that is non-drunk and going to the non-blinking machine of this type. In other words, this is important. It sounds very amusing, maybe, but what the casino is doing is a trap. Because if the person is following their natural gut or their natural instinct, they are getting screwed, both drunk and non-drunk. You parse the numbers, that these are the numbers are saying. Now what we can do is the following. We are there in the casino, the conference, having our drinks and just sitting and saying, oh, I don't want to play. I just copied the parameterization here. And this is unobserved and we don't know. And then we start, don't have anything better to do. And then we decide to do the following. Let's do random sampling in the casino floor. What it means, this is layer one operation. We start drawing samples with our we start drawing samples with our eye, and you follow the person, and you see this person is playing machine X1, and then you take note, and you say the person is winning, Y0, not Y1. Now you get another person, X0, and you do that 10,000 times. You're just having our drinks and fun, nothing to do. Then you get this random sample from this, that is this graph, equivalent to the left side graph in the third slide, and then you get this distribution. Expected value of y given x is equal to 0 is 0.15 of winning, and x1 is also 15. And this is the conclusion of our study. We have so many samples that we even say this is the true number. 15% of the time people is winning. Note here that we don't know, this is the most important of the example, that B and D are playing any role in the game. We just observe the actions, what is the machine that the person is playing, and the outcome, if they are winning or not winning based on this action. But for sure, my claim is like this is happening all the time, because we don't even know why we are acting in some way. These UCs, these variables, you are all the time driving our decisions. You can just observe what the person is doing and the outcome of the action. But you don't know the reasons or the causes that why people is doing something this way. Then it's matching this sense more broadly. Now that's good. Then we are already suspicious because we don't like the environment. And then you call the commission and says, we can feel that there is something shady here or smelly here. Send some inspector because the numbers are not matching the regulation. Regulation says 0.3. It doesn't matter what the machine people is playing. They are getting 0.15 of the time. Then there is something wrong here on the floor. Send your guy. Then they will say, okay, they are getting so many of these calls, and they say, okay, I will send the guys. And then send an inspector. We are very proud to show the data to the inspector, and they say, how did you collect? And say, I just passively collected the data, and I have this huge, and they say, this is crap. You don't understand anything about causality or randomization of Fisher. Let's be serious here, and let's apply the protocol, such as the FDA. Let me do a randomized experiment here on the floor, the casino floor. What does it mean? 2 steps. Still, you collect a unit and you do a random sample from the casino floor, but in the decision time, you flip the coin. That is this guy here. This X here that you are cutting the B and D, you flip the coin. The coin is the one that decides the value of X. He does that a few thousand times. He even do a fancy one based on UCB or Thompson sampling, and he gets the expected value of y of winning given that do x is equal to 0, 0.3, that is the same of y given do x is equal to 1. Interesting case. Now he comes back to us and say, please stop bothering me. Here, I have more important things to do. The casino is kosher, is following the regulation. Do something better of your life. And he leaves the place. That's our paper. You can read the story. I'm very happy that the reviewers allowed that to pass. Because paper is nice, but it was good. Now the question is for us, like, first the question, what's happening here? We have now these collisions because we have these 2 data sets. The natural data set, that is what the real people in the casino floor is feeling, that is 15% of the time they are winning. And on the other side, we have this somewhat artificial, but this thing that is 30% of the time people does get the causal, what is called the causal effect, but no one in the real world is getting that. This is a little bit artificial, but it is the causal effect. Now this is the question, and you say, we are more clever than that. We are like, we took our, machine learning class, then I can do even adaptive. I can do better than 0.3 or 15. And they run all these strategies that we are used to, such as epsilon greedy, Thompson sampling, XP, and so on, UCB. And this is what we get. In the left side is the probability of picking the correct actions in the Y and the number of interactions in the X. And we have the regret here in the right side. Now, if you see, regardless, one of them is coin. It's very small for me, but one of these colors is the coin flip. They're just doing a basic one. Then all of them leads to the same thing. That's 15% of the time you are able to get the correct answer. Why? Because the outcomes X1 and X0 are the same. Then there's no distinguishability. There is no way of picking one. And all of them are equivalent to what the inspector did in the floor. They get the same numbers. Then we thought that we could be clever, but we ended up in the same place. And it's kind of not beautiful type of regret. Now, the realization at that point, this was 95, is like bandits minimize short-term regret based on the do distribution. And all of them are doing the do, as I said. More broadly, I can tell you this today. Now the obvious question here is like, can we do better? Second attempt, let's do something that is proposed in the paper called counterfactual randomization. We propose this thing called the regret decision criterion. Now you use the layer 3 type of quantity. I'll parse here. Y sub x equal to x1 given x is equal to x0. Let's parse what this means. It's a counterfactual, nested counterfactual sentence that's the expected value of y had x being x1 given that x is equal to x0. Then there's a name for this, just for the literature purpose. This is called effect of treatment on the treated. This is in comparison to our original criterion in red, that is the expected argmax of, we're trying to find something based on the y given do x is equal to x. This is the flip of the coin or the UCB and so on, the TS. We say, no, we want to do this y sub x given x0, y sub x1 given x0. By the way, this guy can be written, this was one of the questions in the beginning, as y sub x is equal to small x. This is like personal note, but no effect, just in terms of labeling, some people want to discuss. This is also called a counterfactual. Everything can be called a counterfactual. But it's too weak. This is too weak, and we just call it, this is a layer 2 quantity, and we just call it do. There's no point, because I want to distinguish and get this name for this quantity here, in this particular quantity. This is for literature purposes. But let me make a note. General counterfactuals like that, y sub x given x prime that we call, or ETT, effect of treatment on the treaty, we call ETT. Let me go. General counterfactuals are difficult or impossible to evaluate it from data, even when you can do experiments layer 2, except for some very special conditions, such as the binary treatments, backdoor admissible, there is no confounding, and so on. Then you can go to chapter 9 of causality, and there are other references, and you see that. Now the observation, this we know for many years. Observation in the paper that how can you get data, what we're trying to, that's great. But can you get some way get data that allows you to estimate this kind of quantity? It turns out that it's possible, and the idea will be this idea of the paper. The idea will be the following. Note that the agent that is about to play machine X0, the guy is there, maybe he's drunk, and he's going to play machine X0 with his hands. Here, if you're looking for the one, he's X0. Whenever he's about to play X0, this means that the unknown, there is this unknown function f sub x b of d, blinkiness of drunkenness, that is being evaluated at X0. This is the meaning that he is about to play X0 in English. Now, this suggestion. Let's pause, interrupt the decision flow, and wonder. I'm about to play, I'm an agent. I'm about to play X0. Would be better off going on with my intuition, that is X0. This is what I want to do based on my drunkenness and whatever is in the environment that I don't even know. Or should I go against my intuition or my gut and play X1? This is the meaning of the counterfactual. This is layer 3 guy, quantity. Note that if in this step 2, that is the pause, interrupt the flow, and if you do not interrupt, you don't pass that through your mind, and you just move on and play at X0, this will give the data from the random sampling. This is the P of XY that we are getting. Random sampling. If you do interrupt and flip the coin, as did the inspector, x is equal to rand, that we ended up getting x1, this is the meaning of y given do x1. Oh, 5 minutes? I see 7. I'm Israel, I need to negotiate. And also my Jewish roots. Thanks. If you do interrupt, you get this do x. This is the meaning of the quantity. But if you do interrupt and make x is equal to randomize, that you get x1, given that you know that you're about to do x0, this is the meaning of this counterfactual quantity y sub x1 given x0. That's the observation. Quick comments here. There are decision theories related to, there's many books written about that, a lot of discussions, Newcomb paradox and so on. You can discuss in the coffee. The first one is called EDT, evidential decision theory, that is related to the first type of decision. The second one is related to the CDT, called causal decision theory. And there's this one that we essentially developed and starting this paper that's called RDT, that is based on the regret or the counterfactual. We can show, it's not hard to show that RDT, by the way, it is possible, unexpected maybe by some, but usually expected CDT dominates EDT is not true. There are some settings that EDT dominates CDT. In the Newcomb, it is possible to show that RDT dominates these other two strategies. If you want to be you play put decision theory hat and play this game. Now this is the plot that we get. Same thing, in the right size probability of picking the correct actions by the interaction. This is all the colors I just collapse in red. And now this is the blue, is the one that we are using the intuition, taking the intuition into account and say, I'm about to play X0. Should I be better off going against it? And then you flip the coin. You need to flip. You need to deconfound the situation. Then we are able to restore some type of consistency. And then you can play you can play clever. And now, once you move from, sorry to change the call, this is another paper. Once you move from non-convergence to convergence, now the game that you are playing is another one. How fast can you converge? Then we do kind of clever tricks here to move from this blue to the red. Hopefully you'll be able to do better, but I'm already very happy that you could move from blue to something that converge based on this type of introspection. This is the picture with the tapes. Now in each stage, we are saying that don't do the y sub x or the y given do x. You should use the counterfactual as decision. Let me try to converge. We can do that, by the way. We can do with bandits. Now you can have larger type of models. We can do with MDPs and variations of POMDPs and so on. Let me skip task 4. Checking my website, I have a very nice video that I'm just talking about task 4. But let me move here. I'm going to the conclusions. I was very optimistic. One second. Okay. Summaries here, there are two, this is the second last slide. Summary, first task that we'll talk generalized policy learning. The causal agent, let's call C, Mr. C, as Yuda says. Causal agent learns through different modalities, including by observing and intervening in the environment. And the off-policy, the on-policy, and the do calculus. Talk briefly about this, when and where to intervene. Agent C now contemplates not to intervene in the system. If it does, however, it learns how to surgically change the environment so as to bring about the desired outcome. Counterfactual decision-making, I just mentioned briefly or talked about that, not so briefly, maybe 10 minutes. C is capable of analyzing itself and contemplating that he is about to do something, and then protects against his adversaries, such as the greedy casino. I didn't talk about robustness and transportability, but agent C is capable of generalized causal knowledge acquired in one setting to another with a minimal amount of experimentation by leveraging the structural causal invariants across settings. My conclusions, causal inference and reinforcement learning are fundamentally intertwined, and novel learning opportunities emerge when this connection is fully acknowledged. Oh, there's animation here. In practice, failure is, if you want to be negative or protective, not for love, but because we're scared. In practice, failure to acknowledge distinct features of causality almost always lead to poor decision-making, and worse even without knowing it. Structural models can help to organically understand and cope with the existence of unobserved confounders, which includes these agents' beliefs, intents, desires, and emotion. What we are trying to go towards and need help, but this principal framework for designing causal AI systems integrating observational, experimental, counterfaction, both data, modes of reasoning, and knowledge. And this leads, hopefully, to a natural treatment of human-like explainability and rational decision-making. Thank you, and open for questions. If you...